All right, guys, let's go ahead and go over today's warm-up question, and then we're going to get into our notes where we're going to talk some more about conservation of energy and work energy theorem. And you do have the rest of the assignment that you started yesterday, 902.2 conservation of energy problem set. So the faster we get through this, the faster you can get to work on that, or even to start the next one. So today's warm-up question says, if a frictionless roller coaster starts from rest at the point shown, where will it be moving fastest and how do you know? Okay, so take a look at that image up there. If it starts at the point that I've circled, where is it fastest?
The bottom.
Yeah, the bottom, the lowest point there. It should be moving the fastest, okay, because at that point, all of your gravitational potential energy will have been converted into kinetic energy, so you should have the greatest speed. Now, if you had a longer coaster that had a lot of ups and downs, it's the same concept. You would want to pick the lowest point. If there's no friction, that lowest point is where most of that energy that you started with, that gravitational potential energy, would at that point be kinetic energy. Okay, so again, since it's a trade-off between the two, the lower the height, the less that pie piece is. If you think of those pie charts from the other day, the smaller that pie piece would be for gravitational potential energy. And of course, if you were at like the lowest level, ground level, then of course you would have the greatest amount of kinetic energy because you wouldn't have any gravitational potential energy. So again, yeah, the lowest point. And it goes back to what we talked about yesterday with conservation of energy. Okay, so like I said, we have some notes, and it's going to be a lot of examples like this one. So again, I would encourage you to write down some more of these examples, especially if you were running into problems whenever you were trying to work through them yesterday. This one says, a 0.012 kilogram rock is launched horizontally with a speed of 8.1 meters per second. If the slingshot is held at a height of 1.3 meters, what is the rock's speed upon impacting the ground? Neglect air resistance. Okay, and so they've given us quite a bit of information. We know that we have some horizontally launched rock. We know how fast it's launched. We know how high it is. And it's asking for the rock's speed upon impacting the ground. And we're going to answer this. There's actually more than one way to answer this question. In fact, I could have given you this question in the unit that we did 2 units ago, because this could very well be solved as a projectile motion problem, okay, which you could do. However, we're going to do it with energy instead. Okay, I think you're going to like it better doing it with energy. Okay, so we're going to write an energy transfer equation. I know that this rock initially has both speed and height because it's being launched at a height of 1.3 meters. So I know that I have gravitational potential energy and it has an initial velocity. And so I know that my initial state is both kinetic energy and gravitational potential energy. But when I look at what it's asking me for, it's asking for the speed upon impacting the ground. Well, if I'm at ground level, I no longer have gravitational potential energy. So the only form of energy I should have at the end is kinetic. Okay, and so I can write an energy transfer equation. And guys, if you can't write that equation, you can't answer the problem. So you need to start being able to look at that scenario and figure out, okay, what forms of energy are here? And there's a few questions you can ask yourself. You can ask yourself, is it off the ground? Does it have height? And if you answer yes, yes it's off the ground, yes it has height, well you better include gravitational potential energy. That's a good question to ask. Another question you can ask is it moving? Again, if the answer is yes, you better include kinetic energy. Okay, and then you could also ask yourself, is there something being stretched or compressed at that point? Okay, and then you can include elastic. Now, of course, the question will give you clues because it'll give you that information. But in this question, it only mentions the height and the fact that it's moving with that speed. So it's going to be just those two. It is a slingshot, so if it had given me information about actually pulling it back, like that point in time, then I would have to include elastic potential energy. But this is after that. It's after it's moving. Okay, so after the launch, it's just those two. All right, again, I don't have information in the question in terms of energy. I have it in terms of variables. So Instead of KE, we're going to have 1/2 mv initial squared. Instead of GPE, we're going to have mgh initial equals, and instead of that final KE, 1/2 mvf squared. Okay, and I've highlighted the one I'm trying to solve for because the question wants to know how fast it's moving upon impacting the ground, so I'm looking for that final velocity. Okay, so if I want to go ahead and solve this, plug in my numbers, it looks like this. I have half of my mass, 0.012 times 8.1 squared, that's the launch velocity, plus that same mass times gravity times my height equals my final state when it's at the ground. All that energy should be kinetic, 1/2 times 0.012 times VF squared. Okay, if you can solve that entire left-hand side of the equation, and when you do that, you get 0.54654 equals, and then I have half of that 0.012 is 0.006 VF squared. So from here, you divide both sides by 0.006, and you get that VF squared is 91.09, and then we just take the square root. So the final velocity of my rock upon impacting the ground when it has no more height, that's how fast it would be moving, 9.54 meters per second. A lot easier than solving it as a projectile motion problem, don't you think? Let me remind you what that looked like. Remember this? I could do this. Okay, if you want to do it this way, you can. Okay, you would need to identify your information. Again, it's a horizontal launch, so my vertical velocity would be 0 initially. My horizontal is 8.1 the whole time. I have my acceleration. I have my displacement since I started at some height. That's included. So I have all this stuff. I could find the final velocity in the y direction. I can solve for this using one of my kinematic equations, but even that wouldn't be my answer because if it asks for a final velocity, it wants the diagonal one. So then you'd have to draw a triangle and use Pythagorean theorem and find that hypotenuse, and that would be your answer. But could you do it this way? Absolutely. Okay, do you think this is easier? Probably not. Okay, the other one's definitely faster. Okay, but technically you could answer this either way. Okay, so again, just like all year long, there's usually more than one way to get to our answer. So anyway, if you want to make notes of how to do it this way, you can, but this is going back 2 units ago to projectile motion. All right, so same question, but what if air resistance is present? What do you think that would do to my rock's final speed? It would slow it down. Okay, it would also affect its range. We talked about that before. It'd have a shorter range, but it would be slower when it hit the ground. Okay, air resistance would cause the rock to move more slowly than 9.54 meters per second upon impact because it would cause energy to be dissipated from the system due to negative work done by air resistance. So I would have less energy at the end because some of it would be lost along the way, lost to collisions with air molecules, basically. We'd create heat with that. Now, would it be measurable? Not really, but you would have some dissipated energy, and we looked at that yesterday as well. Okay, and that brings us back here to the work energy theorem. We have talked about this before. Last semester, we kind of started talking about it again yesterday, but just to remind you, the work energy theorem states that the net work done by the sum of all forces acting on a system equals the change in the kinetic energy of the system. And so we can write it a couple different ways. We can say that that our mechanical energy initially plus our net work equals our mechanical energy at the end. We could say that work equals change in energy. That's the same thing, because if I were to subtract this initial energy, I would have final minus initial energy, which is change in energy. We could even include it like this and add only the positive work on this side and then all of our dissipated energy, any of the negative work over here. You could do that. Okay, there's different ways that you could write this equation, and I'm going to encourage you to write it whichever way makes the most sense to you. Okay, so let's see if we can solve a problem now when we're working with an open system. Remember, we talked about systems yesterday. If we have an open system, that means our energy can leave the system. We can have that dissipated energy. Okay, and so this one says a 0.012 kilogram rock is launched horizontally with a speed of 8.1 meters per second from a height of 1.3 meters. That's exactly the same as the last question started. But then it says this, if the rock impacts the ground with a speed of 7.3 meters per second, what is the work done by air resistance? Okay, I already know it's supposed to be moving faster than that. We already solved it a minute ago. So I know that there is work done by air resistance, but if we hadn't done the previous problem, that would be our first question. Is there work done by air resistance? Which in this case you should be able to tell immediately that there is, because this is slower than it started. Okay, but let's write our energy transfer equation. We still have kinetic energy and gravitational potential energy at the beginning, but now we also have work being done, specifically work being done by air resistance. So I already know this is going to be a negative work. Whenever I plug it in, I'm actually going to be subtracting it. Okay, but I have net work, and then at the end, I'm still looking at that speed upon impact with the ground, so it's still that final kinetic energy, and there is no height because I'm looking at the ground. Okay, so from here, again, we want variables. 1/2 mvi squared, that's my initial kinetic energy. mgh, that's my initial gravitational potential energy. Work. It is possible that you would want to put variables in for work if you're asked to solve for force or displacement, because remember, work is force times displacement. But this question doesn't ask us how much force there is, what's the force of air resistance. It doesn't ask that. Instead, it asks what is the work done by air resistance. So we just need the total work. So I'm not going to plug variables in there, okay? But I could if I needed to. And then again, KE, I have 1/2 mvf squared. Putting in the numbers looks like this. Again, mass is 0.012, initial velocity, mass gravity height. Here's my work. And then over here, I have that velocity that it said it's moving, 7.3 meters per second. When it hits the ground, there's that velocity, 1/2 mv squared. If I solve for what I can, again, this whole side over here is still the same number it was in that last calculation that I did, 0.54654, but now it's plus work, equals 0.31974. Again, the way we solved this problem yesterday is we found those two numbers. We looked at what our initial energy was, which in this case is 0.54654, and then we looked at what our final energy was, which in this case is this value, and we said those aren't the same. How do I find how much was lost? And you guys told me subtract. Well, now it's set up to do that mathematically. If I want to solve for W, I just need to subtract 0.54654 from both sides. Now, could you do it the other way and do it step by step and say those aren't the same, let me subtract them? Sure, it's the same thing. Okay, so if I subtract, I'm obviously going to get a negative number, which I expect because I lost energy. Okay, again, remember, negative work means energy is removed from your system. Okay, positive work would mean that it was added in if it was faster than I expected because maybe something pushed it. Okay, but in this case, my work is negative 0.2268 joules. Are there any questions about this problem? Again, this is conservation of energy with work. Okay, now we can add work into the equation, and this is why I told you guys when y'all said, is this a hard unit? I said yes. And it's not because the actual math is hard, it's because you have to write that equation by yourself. It's not on my board, and it's different for every question. So you have to look at that question and say, what's going on? What forms of energy do I have? Okay, questions though? No? By the way, if I had asked how much energy is dissipated, it's the same answer. You would just report it without the negative sign. If I ask how much energy is dissipated, it's implied that it's lost. Okay, but it would be 0.2268 joules. All right, so just as a quick reminder, positive work, work can be done to add energy to a system. Okay, that last example was negative work, but you could have positive work. For example, a desk initially at rest, or is initially at rest before it is pushed for 5 meters with 60 newtons of force, giving it a speed of 3 meters per second. In that case, the work's positive. We had no energy, we pushed it, now we have energy, we added energy to the system. And the amount of kinetic energy that that desk would have would be equal to the work that we did on the desk. And we could say that work was equal to final kinetic energy. That's the work energy theorem, that's what we did last semester. Okay, you could write an equation for it. Again, you had 0 work initially plus the net work that you did equals the final kinetic energy that you have. So your work would equal your kinetic energy. Okay, but again, work can be positive if it adds energy to a system. On the other hand, just like that previous example that we just calculated with air resistance, work can be negative if it removes energy from a system. For example, a 0.5 kilogram ball initially moving at 4 meters per second rolls to a stop after 7 meters due to friction. Again, we started out with kinetic energy, and at the end of this thing, there's no more energy left at all because all of the energy was dissipated. It was all removed from the ball. Now it's heat. Now it's not mechanical energy. It's not usable energy. Okay, that equation might look something like this. The kinetic energy plus that work done by friction gives us 0 energy remaining. Of course, your work there would be negative. You could also set it equal to the change in energy, okay, because you lost all of it. So either way, we typically have been doing it this way, but you could use this dissipated energy method as well. So again, if you have an open system where you have external forces acting on your system, you can have energy added into the system, you can have energy removed from the system, and that's going to mean that you have either positive work or negative work, depending on what's happening with that particular example. All right, so let's try another one. This one says a 3 kilogram box is slid up a ramp with an initial velocity of 4.3 meters per second as it starts up the incline. If the box stops when it reaches a height of 0.79 meters, how much energy is used to overcome friction? Okay, so if the box stops at that height, I know that initially I have initial velocity and I'm starting at ground level, so I have kinetic energy. I know at the end I have height, but I'm no longer moving. So I know I'm going to go from kinetic energy to gravitational potential energy, but I also know that this question is implying that there might be work happening. And so I'm going to include it in my equation, and it's entirely possible that I'm going to have these equal to each other. I have it included here as dissipated energy. I'm going to show you this way. Okay, if you have negative work, you can include it as dissipated energy on this side of the equation. It's the same thing mathematically. If I subtract it to this side, it's the same as adding it to that side. Okay, so either way, whichever one makes more sense to you. So again, it may end up that these are equal. I might have an equal amount of GPE as KE, and in which case I'm going to say there is no dissipated energy. That's possible. Okay, but we're going to see if they're equal to each other. The question implies that they're not. So we're going to substitute in our variables. So KE is 1/2 mv squared, GPE is mgh, plus that dissipated energy if we have any. Again, we're just looking at, and you can do it in steps, is my initial energy equal to my final? And if not, we can figure it out from there. Or you can do it with the equation. Okay, putting the numbers in looks like this. 1/2 times my mass, 3 times my initial velocity, 4.3 squared, equals mgh, there's my same mass, times gravity, times that height that it says in the question, 0.79. Okay, and again, we're trying to see if these are equal. And look, my initial energy is 27.735. My final energy is 23.226. Not equal. Okay, mathematically, if I want to solve for it from here, I just need to subtract. It's the same method that we used a minute ago when we solved for work. Okay, but this time, because I set it up as dissipated energy that I have at the end, instead of negative work, okay, I'm going to get a different sign on my answer. My dissipated energy would be negative 4.509 joules. If I asked you for work done by friction, your answer would be negative 4.509 joules. It's the same answer though, same magnitude. Okay, but again, your work is your energy change. This is how much energy was lost. Okay, so again, you should be able to solve for this. And if you like solving for it the other way with work, do it that way. If you like solving for it this way with dissipated energy, do it this way. You get the same magnitude of your answer. You just have to pay attention to the sign. Okay, because if it's work and it's negative, you need to include the negative sign. If it's dissipated energy, you're just going to give me the magnitude, how much was lost. Questions about this one? No? How much work is done by friction? What did we just say? I forgot I had this question on here. What did you say, Emily? Yeah, negative 4.509. Same magnitude, just we're going to put the negative on to indicate that it was lost. Okay, so the work done by friction, you removed that much energy from the system. Okay, this is the other way to solve it. Okay, I told you you could do it two ways. So if you want to write the equation this way instead, perfectly fine. It's going to give you the exact same thing at the end. I'm not going to do the whole thing over again. It's the same numbers. It's just now it ends you with the negative sign instead. Okay, so depending on which way you write it. Does anybody have a question about this problem? Okay. All right, guys, for the rest of the period today, then, you are working on the assignment that you started yesterday, 902.2, Conservation of Energy Problem Set. That one's due tonight. However, you also have another assignment that's due tomorrow. And if you finish the one from yesterday, I would strongly encourage you to get a head start on the one for tonight, tomorrow, and that is 902.3. That's going to have work in it. Okay, so the one from yesterday just was conservation of energy in those closed systems where you didn't have any external forces. This one, now it's possible that you're going to have external forces acting on your system, and so I want you to practice both. Again, this one's not due till tomorrow, but this one is due tonight, so please make sure that you finish 902.2 first. If you have questions as you're working, please let me know.